So now we're going to solve part D of the equation. It says, now assume that points B and C were not on the same horizontal level. In particular, assume that the surface from B to C had a uniform upward slope, so that points C were still at a horizontal distance of x from B, but now at a vertical height of h above B. Answer the question posed in part C, which was determine the coefficient of friction so that the box comes to rest at point C. So basically what we're doing here is finding the coefficient of friction if the box is traveling at a slope after it hits point B.
So we're going to use the conservation of energy to solve this problem. So that's the kinetic energy at point B plus the potential energy at point B plus the work of friction, because here it's moving, so friction is working and using up some of the energy, equals the kinetic energy at point C plus the potential energy at point C, and it stopped there, so the friction isn't affecting it. So then that's going to be 1/2 mv squared plus mgh, and then minus the force of friction at the distance of L, which would be our new distance, equals 1/2 mv squared plus mgh. And for this velocity at B, we're going to use the same velocity that we found in part B of the problem, because that was the velocity at point B that they wanted us to use. So that's going to be 1/2 m times the square root of 2gh squared. And then at point B, the height is 0, so there's going to be 0 potential energy. And then friction is negative mu mg cosine theta times L. And then on the for C, there's going to be no kinetic energy because it stopped, and the potential energy is going to be mgy for our distance y. And now we're just going to simplify it a little bit. So that cancels with that, the 1/2 and the 2 cancel in that part of it. So that's going to be mgh minus mu mg cosine theta times L equals mgy. So now we want to get mu on the side by itself. So we're going to add this part of the equation to this side and subtract this part of the equation to that side. So it's going to be mgh minus mgy equals mu mg cosine theta times L. So then we can group this part together to get mg, then the quantity of h minus y equals mu mg cosine theta times L. So then the mg cancels on both sides, so now we have h minus y equals mu cosine theta times L. So to get mu, which is the goal of the problem, you have to divide both sides by cosine theta times L. So now we have that mu equals h minus y over cosine theta times L. And since L cosine theta gives the x component of the vector, which is the x part, this x variable, we already know that x was given to us in the problem over here, so it's an accepted variable to use in the answer. This becomes mu equals h minus y over x. So that's the answer to part D of this problem.